For what?
For 1,000.
For 1,000 you got 2. And that makes sense. We're much bigger than the wavelength. It's exactly what we expected if we listen to the previous class. Do you understand what we're doing?
Yes, but I need to reload it.
Oh, I'm sorry. I'm sorry. For the 10, 2.01?
I got 2.02
2.02 for 100 micron. Okay, so this we reached the asymptotic value. What do you get for 1 micron? And don't forget to divide by 2. The size, because it asks for the radius. Do you see how slower it gets as you have more and more, as the size gets bigger? For 1, you got 3.4. So anybody got different values, please tell us. Just so we know, either we agree with these values or we have question marks about them. So once you have these values, what you want to do is multiply these Q's. So now I'm going to take this and make it simpler, simply by dividing by pi d squared. So C star will be, I'll have QC, I'll have a 2 on top, pi goes away, I'll have a d on the bottom, and I have 1,000 kilogram per meter cube. So the answer is going to actually be in kilogram. This is meter square on top, so it's going to be in what am I saying? This is, no, I have per meter because I have d here. So d has to be in micron, no, in meters. D has to be in meters, and then I'm going to have meter square per kilogram. These are going to be the units I'm having. If I use 1,000 here, and I use a d in micron. In meters, sorry, d in meter, diameter in meters. So take these the QCs, multiply them by 2, divide by the diameter, divide by 1,000, and tell me what you got as a C star. 10 to the minus 7. 10 to the minus 4. Third is 0.0068. The
fourth one is 4.02 e minus 4. The fifth one is 4.04 e minus 5.
What? 4.04
E
minus 5, 10 to the minus 5. And the last one?
4 e minus 6.
10 to the minus 6. Okay, so if I have to plot it as function, so this will be diameter. And I'm starting at 0.01, so it's going to be logarithmic. 0.1. I have more room, so let's move it. 0.1. 1, 10, 100, 1,000. And here I'm going to have, similarly, So I have 10 to the minus 7, let's do 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, 10 to the minus 3. Okay, so 0.01, what did you say? 7, 8, 10 to the minus 7. It's almost 10 to the minus 6. Okay, I'm here. 0.1, I'm 10 to the 7, 10 to the minus 4. I'm almost at 10 to the minus 5. My plot. I'm in logarithmic scale, so the differences are actually very large. This is 7, 10 to the minus 3. 7, 10 to the minus 4, sorry. So I'm here. For 10, 4, 10 to the minus 4. I'm slightly lower here. For 100, I'm 4, 10 to the minus 5. I'm dropping to here. And at 1000, I'm 4, 10 to the minus 6. So I'm somewhere here. Okay, so in this logarithmic scale, I get the most bang for the buck for droplets of 1 micron. If I take the same amount of water, I divide it between drop size varying from 0.01 micron to 1,000 micron. This is where I'll get the most attenuation. Do you know how we call this? Fog. Are you getting what I'm talking about? This is fog. This is why you can't see through fog. It's because you're packing, and it's not because there's more water in the air than when it rains. It's because it's in such size of droplets that it's much more efficient in attenuating than if I put it into large drops or if I put it into tiny drops. So depending on how you package material, you can have very different optical effects. Okay? So this is this resonant curve that I talked to you the past few weeks. There's certain sizes that resonate much better with light, those that are close to that wavelength. And our friend Ian here will tell you in acoustics it's exactly the same. If you want a sensor that measures zooplankton, you use a wavelength of sound that resonate with the size of a zooplankton. If you want to do fish with acoustic, you take a lower wavelength because it's a longer wavelength, which is a lower frequency, because that's what's going to resonate with fish, etc., etc. So you have to match your wavelength to whatever phenomena you're interested in studying. Is this clear so far? The second exercise. Do you understand what we did and how the arithmetic gone, even if you did not completely calculate all the numbers yourself? You know how to get there? Because I want to move to populations. So far we did monospecific. Everything's the same. Okay? Can we move to population, or people want to stay on this still? Stop me if I'm going too fast. I don't mind staying on this and waiting. Do you want to stay on this, or can we move forward? We can move forward? Is this okay with you? Okay. So now let's do populations. Now I assume there is a phytoplankton population. They have a certain index of refraction. Again, the same one we used all along, but this means we're in absorption wavelength. We're a diatom-like maybe. And assume we have a size distribution to be a power law. That's not a good assumption for phytoplankton, but it doesn't matter. We can always do, once we know how to do one type of size distribution, we can do any. Okay, so let's assume it's a power law distribution with this differential size distribution that goes like d to the minus 4. Particles per ml per micrometer of size beam. For particles ranging from 0.2 micron to 100 micron. Subdivide this range logarithmically into 35 size beam and assume a wavelength of 440. Okay, so how do we divide something into 35 logarithmic size bins? Okay, so this is, and this can be also data somebody gives you from a Coulter counter. So let's do the other side as well, this way we can. Okay, so I'm having a population. It varies from 0.2 micron, the size of my filter, to 100 micron. And I have 35 logarithmic size bins. I don't know how many I put here, but let's assume it's 35. This is the number, this is the number distribution. And it goes like d to the minus 4. Okay, it's a power law. Power law means on the logarithmic scale I'm going to get, and this is also logarithmic. So first, how do I take 0.02 to 100 and have 35 logarithmic size bins? Anybody has a clue how we do something like this? Looking at Cal. Okay, so one way to do it is to say, well, I don't know exactly what power law, what's going to be my thing, but I know the following. So I have this unknown parameter, I'll call it rho. Rho we're using too much today. Let's use a different one. Epsilon. We love epsilons. And when epsilon is to the 0, I'm at 0.02. But when epsilon is to the 35, I'm at 100. So 0.02 times epsilon to the 35 equal 100. And so now I can find what this epsilon is going to be. And this will give me a power law type or an exponential, it's whichever, it's just a change of basis, equal beans, equal in power beans on my size distribution. So anybody can solve this. What is my epsilon? That will give me, will this be 35 or 34? No, it will be fine. Yeah, because the first one is 0, we get 35. So epsilon to the 35 equal 100 divided by 0.02, which is equal to 1,000. Oh no, what am I saying? 5. It's going to be 5,000. Now you're helping. So epsilon equal the 35th root of 5,000. Anybody know what it is? 1.2755. Okay. So now I have all the position of these. All the position of my, this will be my epsilon to the 0 is the beginning, and then the next one is going to be times, so my diameter, my beam diameter, di are going to be 0.02 times 1.2755 I to the I. Going from I equals 0 for the first one, and then second, and since I'm starting at 0, I'm going to, so this will be for I equals 0 with 1 difference to 35. Now, if you do it for your list does exactly that. This is how the diameters are done for the list. I think it's 1.2 for the list or something like that. And you have 32. Actually, yeah, and the list goes from 2 to 250. But there's a certain value, that's that value, the exponent that you're going to use, this epsilon, such that you have, they get bigger and bigger on a linear scale as you have less and less particle in your population. That's why they do it. Okay, so now I have equal bins like this, so I know how to do them. What?
Was it I equals?
I equals 0 because the first one is going to be at 0.02 I want it to be. That's my that's the smallest size of the bean that's going to go from 0.02 to 0.02 times 1.2755. Then I'll have it from that to the next, etc., etc. But yeah, MATLAB doesn't like I equals 0, so we have to do everything with I minus 1. Okay, so let's open col BH varied size part 2. So col BH, I have to open it. Oh, actually, I can open it from here. Open col BH varied size. And what does it tell me to do? It tells me I have a bunch of, here it is, where it determines what's my interval's going to be and the factor that goes into it, how many beans I'm going to have, what's my Dmax, what's the number of size classes. Here I have 100, but let's do it before that. Okay, so here everything is put straight into the, it's not going to ask us. We're doing everything in the code. So refractive medium is 1, 1.05 is relative to that, and 0.01 is the imaginary. Wavelength is 440 nanometer. Is this what we ask in the Excel spread, in the Word? The number, our Dmax is different, so I have to adjust it. My Dmax is 100 and 0.2. So let's go back and see that indeed that's what we have. My Dmin is 0.2 instead of, I should put here 0.2, minimal size. Dmax, and everything is in micron. Dmax is 100, and I have 35 intervals. Put 35. It's going to do all its calculation on its own. And then I can run it, and it's going to do, what else do I need to put? Does it say, there's information about the size distribution. I have to put n somewhere. No? Save phyto data, and then it plots the Q's, but I don't see it calculating it for, okay. Let's go back to the, I have 5 10 to the 4th. So the first one is going to, so then I have to go, I have first to generate an output that then is going to be read by another one for the population, during this Young population, or power law population, I should have called it. So I have, this is just the one to generate for each bin the output. We can run that just to see what we're going to get. We're going to get outputs for each bin. So here, what we're getting is the QA in yellow here. This is QA. QB, you can see it goes into 1, and then QC. So these are just the Qs for every bin size in my population. And these are relatively smooth curves, so we don't need as many size interval. Probably 35 is good enough. We can double it afterwards to see if it makes any difference. This is QBB here. And here you're getting QBB over QB. We don't need it now. Okay, I'm going to close it. Now I'm going to call open Young population. Young population. It loads phyto data in, and then it's going to do it for the distribution function that's at the top here. F times, F equal 5 10 to the minus 4 D to the minus 3. Actually, we have a D to the minus 4, so I need D to the minus 4 here. Is it true or is it not? D, F is equal 10 to the minus 4. So I corrected that. And then it's going to calculate A for each bin, B for each bin, C for each bin, and then lump them all up to give us the distribution for the whole population, the value for the whole population. So I'm running it. Okay. This is A absorption per bin and backscattering for each of the bins. Then, and C per bin and scattering per bin. So how much each of the bins contribute. Here we have the volume scattering function in figure 1 for the whole, for each one of the bins, but then we add them up based on the size distribution to get the volume scattering function of the whole population. Let's see what else. I think this is it. This is all yeah. And then I can have, it sums them up, so I can also look at what C equals to. The BIM C is 0.1, A is 0.04, and B is 0.06 for this population. So I can take a population of particle, say from the list, and calculate whether that is consistent with my beam attenuation, for example. Just in that case, if I fit a curve, or actually I can put each beam and the values of number of particles for each beam and see if it's consistent. Any questions about this? I know it's a lot to suffer through. Do you understand what I've done? So one thing you can do, for example, is to see if, first thing I say here, compare the phase function of all. This is this plot. You can see that there are a lot of variability for each beam in the phase function. But once I add them all up, I get a very smooth curve. Things don't change a lot. So this is why this resonance curve we talked to you about that you see in the ME code coming out from monospecific population, when we look in the ocean, we very rarely would see them. Only if you have a monospecific bloom will you ever see this type of structure in the phase function. So, and this is why we can use, for example, in hydrolite, relatively smooth curve to describe the volume scattering function. Because in the ocean, we rarely see this type of modulation. What happened? Okay, so now it's asking me what happened if I'm changing from d to the -4 to a d to the -3. Okay, let's say my population is d to the -3 instead. What do you think is going to happen? And I'll have the same number to start with. What? My A, B, and C's, what about them? Should they go up or down? Should go up, because I have more particles in the big range. Okay, what else? What else can I expect to happen? What? Let's see what our BB to B is currently, and let's, BB over B. BB is, okay, I can get BB over B is 0.03 currently. Let's see if that's going to go up. Because when I'm at this steeper population, size does influence my backscatter. This is what I got so far. I got 0.04, 0.03,